Okay, so hello everyone. So it's really a pleasure to be here, okay, thanks to Hans and others to organize all this, and it's very nice to see all those friends. So what I'd like to tell you today is about you know, a kind of statistical view of the history of wavelets. And so I kind of called it how the Gaussian world became sparse. And so that's a theme that we have seen quite, in many of the talks so far. And okay, let's start like that. So this is Brownian motion, which we have seen in several talks so far. And so this is probably the first example of stochastic process. So it was constructed by Wiener in 1923. And actually, the way Wiener constructed it, he constructed it explicitly here by making a sum of random cosine functions. So just from the point of view of the construction, you see it's very much related to Fourier analysis. And now those variables here are Gaussian variables. And so it's a sum of independent sinusoids. And now, what are the very nice properties of this Brownian motion? So it's non-stationary. It's there's some difficulty in having those guys converge, and so that forced him to make it non-stationary. Then there's a 1 over omega spectral decay, and that's easy to understand here because you are dividing by k. So it's like a 1 over k. So that's the Fourier component. And now what's very nice also is that you have independent components. So if you do finite differences of those guys here, so you get something independent. So now, in fact, there's a nice book by Yves Meyer and Stéphane Jaffar on wavelets. Actually there, they in fact indicate that Lévy in 1930, so that's quite some time before wavelets, actually had another generative model of Brownian motion. And if you analyze it, actually you see that in fact there's the Haar wavelet in the background, although Lévy didn't know about wavelets. And there's also the very nice work by Patrick on analysis of, say, Brownian motion, fractional Brownian motion with wavelets. Okay, so now let's go to 20th century signal processing, and that's a sort of cartoon, but in the 20th century, people like very much stationary Gaussian processes, and there's the Caron-Levy transform, so that's the spectral representation of such processes. And then, as Martin also mentioned, in those early days, people were interested in using those models to make predictions. And so that's a typical rate distortion curve for some stationary process. And so what you see, it's sort for predicting compression performance. So you see that actually the Caron-Levy, of course, is optimal. And so everything works very well. And it's also known that, in fact, the DCT, which is used in JPEG, actually asymptotically is equivalent to the Caron-Levy for those stationary processes. In fact, here, so that's also, I go back, while Martin was, experimenting with the first wavelets during my thesis, I was trying to prove that actually DCT is asymptotically equivalent to Caron-Levy for all stationary Gaussian processes, and it's actually the case. So, I mean, that makes for a very nice theory. And now if you look at this diagram, you see that the really poor guy is the Haar wavelet. So it's absolutely terrible. So engineers would never consider those things. And then also there's the classical reconstruction algorithm in the 20th century. Again, it's a cartoon. So they're, let's say, based a little on this paradigm here, which is having a data term, a regularization. And if you want to have it not too complicated, you use a quadratic regularization. You can work it out as a formal solution. But in fact, there's a very nice link with Gaussian modeling. So if now you make the assumption that your signal is Gaussian, and then you can see actually that this solution here, now if you just choose this operator here to be, in fact, the whitening operator. So that's the square root inverse of the covariance matrix of the signal. You see you have a complete equivalence between that and the Wiener filter. And the theory tells you that's the best you can do. Okay, so you're very happy and everything works well. And then came wavelets, okay. So Alex, excuse me, I'm talking about basis here. So then came wavelet basis. So there's Alfred here. So Martin, as he was young and playing with filter banks, and they weren't called wavelets yet. And okay, so those guys here that came up with the multi-resolution theory, and this really launched many, many applications. But okay, what's important here is sparsity. And so Dave was supposed to speak after me, but okay, will be present in the background of my talk. So he's really, I think, you know, the guy who really like sort of, you know, insisted on this sparsity thing. And this then, okay, branched off into, you know, compressed sensing. And so that's, you know, and the advent of sparsity. Okay, so here's what I want to tell you about today. So there's this Gaussian kingdom. I just tell, you know, very brief summary here. Then came wavelets, and I give you a very, very short snapshot of some key messages out of wavelets. And then I'll tell you about sparse stochastic processes. In some sense, this is, you know, a sort of substitute or an extension of the Gaussian models that fits much better with wavelets. And then we'll talk also about, you know, present stuff and future related to that. So very brief, about 30 years of wavelets. So if you want just to sort of remember the key messages, so it just goes against, I mean, some of the things that people took for granted in the 20th century. There's this very simple denoising algorithm. You go in the wavelet domain, you threshold, and you go back. And wow, this guy often outperforms the Wiener filter. Okay, and actually, here to give you some example of the impact, so I put also some cites here, citations from Google Scholar that I collected yesterday. So there's David's very influential paper on wavelet domain thresholding, and this has, you know, like many people have, you know, improved upon that. But I mean, this works often much better than the Wiener filter, so it seems to contradict the theory of the 20th century. Then, second fact, we saw that wavelets, you know, one area of success is coding, and in fact, they outperform systematically the DCT, you know, and DCT is optimal. It's the Caronin-Löw transform, okay? But so the wavelets go better. So here's just an illustration. So here's the wavelet transform of this cat here. And now if we will just wipe out the small coefficients, and you see the cat not much, okay, is happening until you wipe out all the coefficients. And this is really this sparsity property. And again, I mean, this is, even though it didn't make it as an industry standard because of some hidden patents, I mean, it's a successful compression standard. And, you know, the JPEG 2000 Alliance. Then fact number 3, and that Jean-Luc was illustrating very prominently this morning. So L1 schemes, or even L0, often outperforms L2. And so that comes back to my first slide, where you have now this paradigm of solving inverse problems with a data term and a regularization. Now, what you put as a regularization, you exploit the fact that wavelets give a sparse representation. So typically, we would like to penalize the L1 norm of the wavelet coefficient. So there are also, like, you know, very influential paper that showed actually that could be solved very nicely by using iterative thresholding algorithms. There's also total variation, and so which is imposing this L1 norm on the gradient, and of course compressed sensing, because I mean, this is the main, you know, way one is using to reconstruct signals in compressed sensing. Also note the number of citations here, so that you'll see that compressed sensing is, you know, overtaking wavelets. It's all I will say about compressed sensing today. But okay, so now, so we have a few important facts here, so that we have this nice 20th century theory with Gaussian, and now we have all these observations from wavelets, and they seem to contradict, all the optimality results we have with Gaussians. And of course, I mean, it's easy to explain because the stuff is not Gaussian. But Gaussian still is very nice because it allows you to derive algorithms. So what we would like here really have a stochastic paradigm that actually predicts the kind of behavior we're observing. I'm not saying that those models should look like images or whatsoever, but they should at least explain like those three facts I explained to you. And here actually, this goes back far in history, is actually Lévy. Okay, so Lévy now constructed Lévy processes, as the name suggests. And in fact, they are non-Gaussian generalization of the Wiener process, so they are non-stationary. In fact, they have also the 1 over omega type of behavior. So if you only look at the covariance spectrum, they look exactly the same as Gaussian processes. They also have independent increments. But now what's important here, though, they have much different distribution. Actually, they're infinite divisible. So here's the guy that Martin likes because it's a finite rate of innovation process. So that's the compound Poisson process that is piecewise constant. So it is an example of Lévy process, and this you could say is the archetype of the sparse random signal. Okay, so now here's the way we like to look at the Lévy process. Of course, it's not the way Lévy was presenting, because in fact the distributions were invented by Schwarz, who was his son-in-law, so that came after. But so what you can do, actually, you can introduce continuous domain white noise, and so we call that Lévy noise. And in fact, it's this underlying is this stochastic differential equation. It says the derivative of a Lévy process is a white noise. But already saying that, it's I mean, kind of dangerous mathematically, because actually Wiener proved that Brownian motion is nowhere differentiable. Okay, so here you're differentiating. Okay, so that can only make sense in the sense of distributions. And the other thing, you also have an unstable differential equation. But anyway, this can be handled. But you have to look at it in the framework of distribution theory. So what you do is, let's say, well, formally you could like say, okay, S now is the integration of a white noise as given here. And now to make sense of that, you need to make inner products with test function as is completely standard in distribution theory. And then you can look at different type of noises. So Gaussian white noise, continuous domain, impulsive. So this is the Diracs that Martin was telling you about. So random Diracs with random heights. Actually, it is a white noise. Or other stuff that's actually very interesting that I will tell you about. And so you get different type of processes. So this guy is non-sparse. And actually, we can prove that all the others are sparse. So that's very interesting. And I mean, here you need to rely on a Russian theory developed by Gelfand. So it's the theory of generalized stochastic processes, just sort of, the counterpart of distribution theory applied to stochastic processes. Now, let's go to wavelets. You all know that wavelets, actually, they behave like derivatives. So here's the Haar wavelets. Now, I don't know if you have noted, but that's the important part for my story. There are other functions here. Those guys are called hierarchical basis functions. They are triangles. And actually, the wavelets are the derivative of those triangles. Okay, so that's important here. The wavelet is a derivative of the triangle. Now, using that, actually, you'll see it's so easy to analyze Lévy process. So you want now to take a wavelet transform of a Lévy process. So it's doing the inner product between the Lévy process and the wavelet. Now the wavelet, we know it's the derivative applied to some kernel, the kernel being the triangle. Now by duality, you move the derivative on the other side. Okay, so it's the dual of a derivative is still a derivative, it's minus the derivative. And what you get? Hey, you get Lévy noise. okay, by definition. And so actually what you are doing, you are just looking at noise through triangles. So here you can deduce many things right away. You see the triangles don't overlap. Okay, the wavelet coefficient are dependent in the scale, but also the other thing that, you know, that wavelet people know, I mean, the across scales, across scales they don't overlap. Okay, across scale they overlap here. So there is a dependence here. So it's independent like that, but there's a dependence across scale. But anyway, with that we really get an understanding what's a wavelet transform of the Levy process, and then we can do this Mterm approximation. Now, this is nonlinear approximation, not exactly like in Caron and Levy. We just take the m largest term and look at the error. So here's Brownian motion. And now I'm comparing dct in red, undistinguishable from Caron and Levy, and Haar. Okay, Haar is not as good. Okay, otherwise Caron and Levy would be wrong. But it's not actually so bad. Now, finite rate of innovation. So the compound Poisson process. So here, okay, Caron and Levy is good at the beginning, but at some point, Haar becomes really, really much, much better, and you know, completely, you know, works much, much better. So that's already, that everyone knows that wavelets work well for piecewise constant. Now, more surprising. And there are those other, let's say, very sparse processes, and here it's the Cauchy process. Now here, actually, Haar is better all the time, and so those guys. So I will make an argument that they're even sparser than those. Okay, so then what we did, we wanted to generalize that, and in fact. Again, it's using this generalized framework. Now, the hard part, actually, of this theory is define what's white noise. And so there we are kind of lucky that, people have done that, very esteemed mathematicians. And so you can define white noise in the continuous domain, and one example being those random Diracs. And then, actually, you have this equation, LS equal W. It's a generalization. The idea being, instead of the derivative, like for Brownian motion, we can put actually any operator, any differential operator, provided that it has an inverse here. And that's an important property. But actually, and how do we invert an operator? In fact, here we're very lucky. We can rely on spline theory, which is what people have done. You know, in spline theory, to characterize all the operators that can be inverted here with the help of green functions, etc. So then here you get your, at least formally written here, S equal L minus 1W, and here you have your sparse process. So now the question is, how do you, for example, observe this process? So you will apply like test functions. And it's the same as the white noise. Actually, now, the interesting thing, I use the same trick as was before the Levy process. I can take this operator, I can move it on the analysis function, and then actually you see that observing the sparse process on the other side is exactly the same as observing a white noise. It's just you change the function here. But since actually the description of the white noise gives you all those statistics, in fact, you automatically have the statistics on the other side. And of course, if you put a wavelet, you can directly determine the statistics in the wavelet coefficient. That's very important because you have a complete characterization of the statistics in the wavelet coefficient, so in the wavelet domain, so we can really say if our thing is sparse or not. Okay, so now the main message, in fact, this is an important message of my talk, is all the probability laws of those sparse processes are infinite divisible. And I'll tell you what it means. So we can take almost the axiomatic point of view here, because the important guy here is the white noise. And it's a little hard to say what is this white noise in the continuous domain. And in fact, we have just 3 axioms, and they're very simple. The first is that you can observe your white noise, not directly, because it makes no sense, but by doing an inner product with a test function, so a function in the Schwarz's class. The other thing is the noise should be stationary. So if I move the test function, I get a random variable. It should have the same distribution for any position of the test function. And then there's also an idea of independence. And so independence means if I take two test functions that don't overlap, I get two random variables. They should be independent. Now, what's remarkable, based on those three axioms, you can actually show that all the statistics of those guys have to be infinite divisible. For any function, and actually that you can also observe this white noise with functions, in fact, that are not necessarily only in Schwarz class, but that can be in LP. And now let me tell you what's infinite divisible. Actually, infinite divisible is an idea. It's like the name says, if you have a random variable, you can kind of subdivide it in smaller variables that are independent, so that actually in distribution, the variable should have the same distribution as the sum of, n. I mean that you can decompose it as a sum of n independent random variables that are equally distributed, and that you should be able to do that for any n. Okay, so you break it down in smaller variables. So in fact, it's very simple to see once you have this white noise, because let's observe the white noise through rect. Here's the white noise. Only an engineer can draw it. Okay, so I'm an engineer. It's okay. Because it makes no sense. It's a very rough thing. Okay, you put your rect. You chop your rect in small pieces, like here. The pieces are non-overlapping. Therefore, those random variables here are independent. And you can chop your rect in as many pieces as you want, so it shows it's infinite divisible. Okay. So this is, if and only if. Now, what are infinite divisible laws? Well, Gauss is part of the story. It's the, that the sum of Gaussians is a Gaussian, so everything works well. But it's the only non-sparse guy of the family. So Laplace, which people have used a lot to justify wavelet, L1 algorithm, is also part of the story. In fact, it's the second guy after Gauss, but that's not too sparse. Actually, it's not very sparse, Laplace. Now there's a compound Poisson, and this corresponds to this random Diracs. So it has like a mass distribution at 0, so it has lots of zeros, but otherwise relatively heavy-tailed. And there's other stuff, like, and the other stuff is very intriguing. That's not finite rate of innovation for Martin, so there's many sparse guys that don't have finite rate of innovation, but they have very, very long fat tails. Okay, so let me show you some examples. So now you have those noises, but then you can just apply this operator L minus 1. And for example, if L is a fractional derivative, so in the Fourier domain, it's like j omega to some power. And all this can be made, very clean. If you solve that, actually you get exactly the Mandelbrot fractional Brownian motions. Here's a Brownian, but now if you increase the exponent, it gets smoother and smoother. And so that's the Gaussian world. But you can also take the same operator and, in fact, introduce the Diracs of Martin. It's also white noise. And what you get, okay, Martin would say finite rate of innovation. I say a spline, okay. But, okay, you get a spline. But it's a non-uniform spline, and actually the knots are at the position of the Diracs. Now, those guys have exactly the same power spectrum. These guys are extremely sparse. Those guys are not. Here's the aesthetic version, so we call that the Mondrian process. In fact, there's even a screensaver for those who have Macs that generates those things. So here's just the operators dx dy. We can do that in 2 dimensions. So just so those are the kind of images we just saw in the previous talk, but those are sort of Brownian Brownian fields, but you can also do it sparse. So no, those are not microcalcifications. But anyways, they're like kind of singularities. But in fact, when you increase the regularity, they become very, very, very similar. But I mean, those guys are sparse, those guys are not. Okay. So this is a sparse stochastic process. But now let me tell you a little what you can do with that, and that's trends, present, and future. Well, you can do signal modeling, but okay, I don't have the... yeah, I'd like to have you listen to the sound. Is there... Well, never mind, never mind. Okay, so that's a Gaussian process, and actually this is solution of a stochastic differential equation where you have this kind of operator. So it's an ordinary differential operator. Now, if you excite it with, let's say, alpha stable, you get stuff like that, and it's much, it's not as diffused, and you can do sums of those things. So maybe you can listen a little. Here is the Gaussian guy. It's called A minor. Do you hear? Okay. So that's the Gaussian guy. So it's just A minor chord, so we have resonance at the A minor. So now is the sparse guy. Oh, where are you? Like chimes. Now what's interesting, you can do MP3 compression on both. Gaussian, it's a catastrophe. The chimes, perfect. Okay, so I'm not saying it. Real signals are like chimes, but okay. At least it has. So now what can we do with that? Okay, so for example, we can justify those L1 type algorithms. If we have a inverse problem, so we have a differential stochastic equation here, what we can do now, usually one kind of just projects the physics on some finite dimensional space. Now here what we can do, we can also project the statistical model onto the same finite dimensional space. And then, in the discretized version, actually, we have something equivalent to this Ls equal W. It's just U equal Ls. And if we're lucky, this U will be independent or approximately independent. And then we know the distribution of the U because it's infinite divisible. And then we can write the maximum a posteriori estimator. And that looks very much like what Jean-Luc was showing. And in fact, the operator we can even replace by wavelet because we know the wavelet will sort of approximately decouple. So then we have a potential function. Now we can look at the potential function that are associated with those infinitely divisible laws. So if you put Gaussian, you get the 2. If you put Laplace, you get the 1. Now, if you look at the heavy tail, so the student or alpha stable, you get a log. Actually, Jean-Luc was talking about LP relaxation. There are some papers by Emmanuel Candes and others where they've shown that actually LP relaxation, when you do it as p goes to 0, it doesn't converge to L0. It converges to log. Okay, so that's, let's say, LP relaxation is also part of the story. And in fact, you have this iterative soft thresholding algorithm. You can have almost a generic algorithm. You just change the thresholding function that is the prox that will go with those guys. So it's rather generic. Now, if you have a stochastic model, actually what's nice, you can go beyond map. In fact, you can aim at the optimal, which is the minimum mean square error solution. So that's usually very hard to do. People, maybe it would require Monte Carlo simulations. But anyway, this minimum mean square estimation, for example, for a denoising problem is just a conditional mean. And for example, with Levy processes or Markov processes, in fact, we can solve that exactly using belief propagation algorithms. And then it gives you a gold standard. And for example, here are for the sparser kind of guys. Now you see here the Wiener filter doesn't work very well. Then TV works pretty well. So that's sort of L1 L1 on the finite difference. I mean, that's what decouples the process. Or the log would be like L0, but the MMMSE works, I mean, it's the best, okay? Now that's a nicer thing even. And actually, when I showed that to Lévy, he was pretty impressed by that, that actually wavelets, for those processes, you can show that they're almost like independent component analysis. And for example, if you have the alpha stable, so you have this model here. Now, if you want to do an orthogonal transformation now, okay, you have this model here where this U's here would be independent alpha stable. Now, what's kind of remarkable, you can, in fact, evaluate the mutual information in closed form, and it's given by here, and it involves the alpha norm of the matrix, and you have this orthonormality condition here, and then we can run an iterative gradient algorithm to try to find the independent component that would fit our process. Now here's the surprising thing, and okay, so here we have alpha stable. With alpha 2 it's Gaussian. So here's non-sparse, and as you go here is sparser. And here what do we have? Mutual information. So if it's small, it's good, okay, because it's very independent. And now here in purple is this ICA, okay, obtained by running this. So it's the best possible solution. And now who is the green guy? It's Haar. So you see that for very sparse guys, actually the Haar is undistinguishable from ICA. Except at 2, because at 2 we know that it is DCT. Okay, so here's DCT, and you see that at 2, okay, I mean it wins. And so there's some range here, you know, where really like wavelets become really optimal. Now we can look at other non-self-similar processes. So for example, AR1 process. So what's interesting here, some years ago, you know, we were interested in constructing different wavelets that would not act like derivatives, but any differential operator. And so we were successful. And here is, for example, the wavelet that goes with a Markov process with some parameter alpha that's non-zero. And in fact, they are orthonormal basis. They also satisfy a kind of multi-resolution, but not by dilation. And those guys are piecewise exponentials. And so they go exactly with this operator. And if the alpha goes to 0, you find Haar. Now, we redid the same experiment with those guys. So in purple is this ICA. So that's, you know, the numerical one. And in green are those wavelets. And they are almost indistinguishable from ICA. In blue are Haar. Okay, sorry, Haar, it doesn't work here. It's not really matched to the operator. And in blue is DCT, which of course works with 2, but not otherwise. Okay, last thing. Those guys are called sparse processes, and people have always asked me, why are they sparse? I say, oh, yeah, well, they look sparse. Now here is a first theorem that proves that they are sparse. And so if we actually take a stochastic differential equation that's now driven by alpha stable noise. So we have this operator. So it's a differential operator of order n. Now, very recently, we have been able to prove actually that those guys are in a Bezov space. And a Bezov space that depends on 1 over alpha, where alpha is the sparsity index of the alpha stable. And there's much more work to be done here, but I mean, this shows that this works. And in fact, this implies that you have a Mterm approximation property for those guys. So they really behave like they're supposed to. So at least now we have a statistical model that's simple, that contains Gaussian, and you know, that explains the way, you know, what people have observed with wavelet. So what's very important, and here I completely concur with Martin, we need continuous domain. And so that is a continuous domain. It's not just reverse engineering, you know, it is really a continuous domain. It is completely backwards compatible. Actually, if you want, the model is just filtered white noise. The secret is the white noise you put. Okay, and it's either Gaussian or the other stuff. And actually, in continuous domain, there are no other white noises. It's the complete class of white noises. And the only one that's non-sparse is the Gaussian. All the others are sparse. And this has this Gaussian versus sparse behavior. Now, also this says, what is a good wavelet? Actually, the good wavelet is the guy that acts like an operator, like the operator, because it will undo this mixing, you know, this differential equation. So you will try to go back to the innovation. And you also see that, you know, if you want to do compression, I mean, it needs to be orthogonal and shortest possible. So actually, it exactly fits the paradigm that one should have short wavelets. Practical relevance, well, it gives you a principled approach for deriving algorithm and guarantee of optimality. Again, I'm not claiming that anything in the real world is like those sparse processes. I'm just saying those sparse processes give you a rigorous framework, and if you crank through it, actually you find all the algorithms that people have been using so far. And you also have guarantee of optimality, so you can at least test how close you are from the optimal. And the current challenges, so is to make the link with approximation theory, Bezos spaces. Maybe you need some you know, new functional spaces to get finer characterization. The practical challenges for engineers are how do you identify the operator L? How do you identify the Levy exponent? How do you compute MMSE solutions, etc.? So there's lots of work to be done. Now, maybe that's my almost last slide. So, you know, Gaussian versus sparse. Now, if you know, in my family, there are quite a few artists. So, so if you look on the Gaussian side, actually, the guy that fits best is Pollock. And now, I mean, it's very stereotyped, but okay, the Pollock here. So on the sparse side, it's obvious. So it's Mondrian. Okay. But now if you're a signal processor, so Fourier here, of course, I mean, those guys are some of random sinusoids, and here, wavelet analysis, okay? And you know, if you put the people here, you could put Wiener on this side and Lévy. You know, so those, and I mean, again, it's a sort of, you know, like caricature, but I mean, those guys, you know, at two extremes. And that's a little what, you know, has come out of all those stories. And last, okay, shameless advertisement. But if you want to read a little, there's also a little about the history of Levy is kind of interesting. So this book, actually, you don't need to go to a Russian website to get your free copy. You can just go here, or you can download it. Or you can buy it, okay, because it has a nice cover by my sister, okay, who's the artist. Okay, thank you very much.